Okay, we're going to talk about BJTs, bipolar junction transistors. So, welcome to semiconductors. Yeah, pretty cool things. We already kind of touched on the diode, and we know that the diode is actually an NP junction, and we were kind of good with that. I think all that made sense. And there was that concept of forward biasing and reverse biasing, and the current only goes one way and not the other way. What I'm actually going to do is add another junction, and it's going to get even cooler. All right, so I'm going to do an NPN. Yeah, what does that do? Well, we have to connect to one of these, so I'm actually going to connect over here, and now we have a device with 3 connections. Actually, they have names, so let's name them. This is called the collector, this is called the base, and this is called the emitter. And what happens is that if I were to connect power here, actually let me put a load here, and then I'm going to put power here, and I'm going to call that VC. So it's the voltage into the collector. And if I actually put some kind of voltage here, then current could go through here if this was, say, connected to ground. So it's like a switch. Yeah, it's almost like actually like a relay. So what I'm doing is I can put just a small signal here. I'm actually going to put a resistor in here because I want to limit the current going through here. And then I'm going to do this, VB. So now I've got my 2 voltages, my base voltage and my collector voltage. And I kind of have a load here, some kind of resistor of some type. Okay, now if I were to put power here, then current would actually go through here, and actually we can study the junctions and we understand the kind of the forward and reverse biasing of things. So let's just take a look at the PN junction that exists right here. I know that that will be forward biased if that's more positive than that, and we can see that it is actually, because I've got voltage here. Let's say that's 5 volts. So that's 5 volts. So right now I haven't put a switch there, but that's okay. We'll put some logic into here a little bit later. Right now, I'm seeing that if current is more positive, or my voltage is more positive here and negative there, then current will flow there. And I know that because I'm good with PN junctions, and so are you, and you're good with that. So now what's happening is that this kind of current here kind of piggybacks on that concept and goes and continues through here. Now, I won't go into the depths of what's going on here electrically. Maybe I'll do that in a different video, but I want to get into the technical, how do we actually use these things and do the math and control stuff with them. Okay, good. So we know now that if I were to put current through here, current goes through there. And the cool thing is that this current can be really, really small. In that it can be like 100 times or up to 300 times smaller than the current that I want to run through here. So let's actually put something in here. I'm going to then say, I'm going to put a motor in here. I want to control a motor with maybe a sensor. And that sensor can only really give me maybe, I don't know, like a milliamp. Really low current coming out of my sensor, but my motor requires a lot more. Let's make my motor 250 ohms. Okay, now let me make this 10 volts. So I want to control a 10 volt motor, and it has a resistance of 250 ohms, so it'll require about 20 milliamps. And then that 20 milliamps is going down here. I want to control that 20 milliamps with like maybe a tenth of a milliamp, like a really small amount of current. And I can do that, say I had a sensor that was actually giving me a really, really low current. I could then turn something on that required quite a bit of current, 20 milliamps. Okay, now let's take a look at what the values are and actually take a look at the math and see how we would do that. First, let's actually put some control in here. Okay, so I'm going to put a normally open push button there, so if I press that, it's going to go down. Now, what resistor do I put here, and how do I calculate this? Okay, let's unpack the actual math and see the formulas in place. First thing I want to do is I want to study the current that's going through here and actually do the math and see the formulas, but I have to understand the voltages really to do that. And we know that Kirchhoff's law says that the voltage drops in series equal to source voltage. Well, there's a voltage drop here that we haven't talked about. It's actually a voltage drop that actually goes from here to here, and it's 0.2 volts. It's around 0.2 volts. It fluctuates to some degree, but it's pretty small, but we still kind of have to take it into consideration. So if I wanted to know the current going through here, okay, so I'm actually going to call that IC. I need my VCC minus my V, ready, CE, because that is my C and that's my E. That's my collector and that's my emitter. So the voltage drop between the collector and emitter is 0.2 volts. Now, also in this case, my current is going to be this resistance here. So that's my resistance of my load and or the resistance of the collector, depending on what you're looking at. Now, I could also write resistance of the motor there because I'm driving a motor. Maybe let's do that. Okay, good. So now if I throw some numbers in here, 10 minus 0.2 volts divided by 250, and that is 39.2 milliamps. 39.2 milliamps. I estimated 20. I was pretty close. Okay, so now we know that if this were to be on, in that it would be like a relay allowing current to flow through, that current would be 39.2 milliamps. Now, let me throw this concept at you about gain. Yeah, it's actually something called beta, the gain of this thing. So what is the beta? So the beta symbol looks like that, and the beta in this case, let's say that's a 200. Now, gain is a concept of that what amount of current is required to have enough current going through here. And that is when this thing is in saturation, right? So let's take a look at this chart and unpack what saturation really means. So essentially what's going on here, we've got our NPN junction, and we know that we've got one junction there and one junction there. And we know that if current is going from here through there, then current can go from this end all the way through here. And as I said before, I'll unpack that in a different video or go look another video up. I want to continue with kind of the concept of how to do the math here and more specifically right now I'm talking about saturation. So essentially what's going on is that we can look at this thing in kind of three different modes. Right now we're looking at two modes, either on or off. Now there's this kind of concept in the middle that's an active mode, which we will talk about next week. But right now I just want to kind of focus on these two modes. So essentially they're about the reverse and forward biasing of these junctions. Right? So it's really important to kind of just pay attention to the reverse and forward biasing right now. So right now, essentially, if we're looking at this junction right here, and if it's reversed, and if this junction is reversed, it's an open switch. Essentially, nothing's going on. It's just open. Nothing's happening. But if this junction over here is forward biased, and this junction here is forward biased, then it's a closed switch. But not only closed, it's like fully closed. Like, it's as if the switch has the ability to kind of close a little bit or a lot. And that's actually the active region. We can actually close it. We can kind of throttle it, kind of like a throttle valve in pneumatics or something. We can actually throttle the amount of liquid and or air, more specifically in this case electricity or current, that can flow through that. But right now we're looking at it as though it's fully saturated and closed. So that's what full saturation is. If we're not fully saturated, then essentially it's just kind of, it's throttling the current that's going through. And again, that is this active region when we use it as an amplifier, which is really cool. But we won't talk about that right now. Okay, so let's continue here. And this is just the example here of what's going on. And in the video, I actually labeled my VC up here as just VC. It should be VCC, and that should be BB, but I think maybe you're getting that. Anyway, okay, so that's saturation, and really, again, we've got these different modes, and saturation is the concept where there is just, it's a fully closed switch. Okay, now I think we understand the concept of saturation in that the current through here, if it were to be this, it would be fully saturated. To fully saturate this guy, I'm going to need 200 times less current going through here. Okay, well, how do I calculate that? So what's my IB? Well, I know my IB is going to be my IC divided by my beta. So in this case, I'm going to take 39.2 milliamps and divide that by 200, and I'm going to get 196 microamps. Pretty small, like super tiny. All right, so now if I need 196 microamps to go through here, what size of resistor do I need to put in there to make sure that that current exists? Now let's figure out what size of resistor we're going to use. And to do that, I want to start with Ohm's law. Now I know that I know what the current should be, and I know the formula for current is, the current is voltage over resistance, but what voltage and what resistance? And then I'll end up solving that for resistance. But let's kind of unpack it this way. So now what's the voltage? Well, it's the voltage drop across this and the nature of that resistance. But what is the voltage drop across this? Well, it's this voltage minus this voltage. And what I mean by this voltage is, take a look, it's a PN junction. Yeah, every PN junction is 0.7 volts. Same in a transistor as well. So this voltage drop across this resistor actually looks like this. It's the voltage minus the voltage of the actual source, the VB, minus, in this case, the BE, right? The BE, so the BE junction voltage, which is 0.7. And in here, my R is my RB. So my RB. Okay, with that said and done, let's rearrange this to solve for R so we can figure out what size of resistor to put here so that I can have the right amount of current so that this thing's fully saturated and my motor's on. Okay, I've rearranged my formula for RB. So now I can solve for the amount of resistance there that will give me this current so that this thing will fully saturate. So when I throw the numbers in here, I get 29.1 kilo ohms. That's pretty high. Okay, so that's fine. So if I actually went and get exactly 29.1 kilo ohm resistor and I put it there and that was 5 volts, then this would be fully saturated and the motor would fully be on. But you know what? I'm going to kind of overload it a little bit because although my gain is 200, right? If I actually get current going through here that's more than this, it's still okay. It's not only saturated, but it's like fully closed. It's almost like closing my transistor kind of like this, if I give it just enough. But I want to like close it a lot. So I'm pretty much going to double the current, or something even more than that. So 29.1 kilo ohms, well, you know what, I'm just going to go for like a 15K or something like that. If I put a 20K in there, I'd still be okay. So whatever's in my kit in between 15 and 20K, so I'm actually going to turn this into either a 15 to 20 kilo ohms, and then I'll have definitely enough current. So let's actually recalculate just to make sure that if I were to put a 20 kilo ohm resistor in there or a 15 kilo ohm resistor in there, I would have enough current. Okay, now I got a 15 kilo ohm resistor there. I want to calculate the base current. So my IB is going to be my VBB minus my VB divided by RB, and in this case we know that is going to be 4.3 volts divided by 15 kilo ohms, and that equals 287 microamps. Yep, 287 microamps. Okay, we needed 196. We have way more than 196. We're good. So if I press this button and close that, then this extraordinary low current is actually going to control this current, which is almost 40 milliamps. That's really cool. So transistors are awesome. That's an example there. The next example I'm going to do, I'm actually going to use the proper symbol for a transistor, specifically for an NPN bipolar junction transistor, which we will focus on. We'll touch on PNPs a little bit later. But for now, let's just control a motor and get a little bit more specific. Let's talk about the type of motor and actually the specifications of the motor and the gain and why the gain is what it is, and we'll have a really good example and you can really see the math work. Let's go over a BJT application as a switch. We're going to drive a motor, a little small motor, and we'll use this BJT here. It's an NPN and it's a ZTX696B. And we'll talk about why I chose that for this application. But what I'm going to do first is just let's look at the circuit. So what we have here is we've got this current that's going through the motor and it's going through the BJT, and when we use it as a switch, we know the BJT is going to be working in saturation. To fully saturate it, then we've got this current going through here, our base current, and it's going to go through here, and it's going to be balanced to the point of, we're going to put this gain into it. The gain is 100. But essentially, the current that goes through here has to be 1/100th of the current going through the collector. Good. So let's actually walk through the steps, but first let's just take a look at what's going on here. Okay, look at this motor. This motor is it's a pretty cool motor. It's a little tiny motor. I got a motor. Oh, yeah, it's right here. That's where I was like, where's that motor? It's about that big. I just pulled this out of my equipment drawer. But it's a little tiny motor. It runs at 200 milliamps, but let's just take a look at the data sheet. Okay, so what I've got here is I've got this little guy. It's a 12-volt motor. Look how fast it's going. Whoa, it's getting 10,000 RPM. That's pretty good. That's pretty fast, eh? Okay, so it's going that fast, and it's a 2.4 watt motor. What I did was I calculated the internal resistance, because resistance is a number that actually we want to use in our calculations. The data sheet doesn't actually have resistance on it, but it's got power and it has voltage, so I calculated resistance from there. Cool, so that's the motor. Let's talk about the BJT. So this BJT here is a BJT, it's an NPN, and you can see, I guess I don't need to put that on the board, you can see that the collector current max is 500 milliamps. Just a little bit, but that's okay, because all we actually need is 2. So we're good with that. So the other thing over here is that, yeah, it's an NPN, and what else do we see about it here? Actually, there's nothing actually on here. This is a screenshot from the DigiKey website, but let's actually delve into the screenshot, into the actual data sheet that I pulled off DigiKey. And let's take a look at that. So if we actually look at the data sheet, we can take a look at the gain. And you can see the gain is 100 minimum. Yeah, so that's the smallest amount it can be. Before we continue looking at the gain, let's just look at some other things here. Oh, it looks like the saturation, the current to emitter saturation is not 0.2. Sometimes it's 0.3, sometimes 0.4, but in this case it's 0.25. So we have to note that, and I wrote that here because it's important, because it's going to go into our math. The other thing that's actually interesting about this guy is if you look down here, look at that. The base emitter voltage, it's 1.2 volts. So we also have to put that, I think I put 1.5. Oh, I did. Okay, well, we'll just roll with that because I've already done the math. We'll pretend. Okay, so 1.2 volts is the emitter base, and we know that that number is usually around 0.7, or at least that's what we've been looking at in class, but that value changes as well. Okay, so back to the gain. Let's take a look at the gain. I actually want to take a look at like the actual how gain changes. So if we I just ripped it off. If we look at the gain chart, okay, you can see that it changes quite a bit, and there are two graphs on here. One is for a really hot gain, and the other is for a cold gain. 25 degrees Celsius is something that it's going to be operating in. It's not going to get that hot. We're not pushing it. We're not asking it to have a lot more current to go through that than it's designed. We're not even going in. We're going about 40%. So if we take a look at the gain, on this one, it's really stable. It doesn't change a whole lot. But as we can see that as the current in the collector increases a little bit, the gain does go down some. Okay, so this is pretty stable. So actually, just take a look at that. Take a look at 200. So if we go up to 200, we're crossing the gain line at just a little bit over 100, but you can see that the gain actually goes below 100 as well. So if you're pushing this thing to the maximum amount of current that it can take, then your gain sneaks down a little bit. But we're good. We're way underneath, so we're going to go with a gain of 100. Okay, cool. So let's actually do the math. Now, you know the first step is we have to calculate the saturation current, which is also the current that's going through the resistor, or in this case, it's the motor. So, step one. We have to calculate IC sat. We have to calculate the saturation current. And in that case, IC sat is going to equal the voltage drop across this guy divided by its resistance. Is that okay? I mean, it's Ohm's law. But the voltage drop across that is just a little bit different. We have to do VCC minus VCE. This is just a little bit of a number here, but it actually makes a bit of a difference. Okay, and that's divided by the resistance, in this case, of the motor. So right there, I've already calculated that to be 196 milliamps. 196 milliamps. So we know that that is the current, the saturation current. Cool. Okay, now for step 2. Step 2 is we need to calculate the current going through here to make that happen, and we do that with the gain. So in this case, it's the IB, and we know that IB is going to be my IC divided by my gain. And in this case, I've got, what again? 19.6. Oh yeah, it's easy, just move a decimal. 19.6 milliamps. So just a small amount, it's actually 1/100th, right? So we now have to figure out what resistive value is going to give us that current. That's step 3. Well, that's a 3 looks like that. Okay, step 3 is calculate RB. So RB is going to be using Ohm's law, the voltage drop across the resistor divided by the current going through it. Now we know the voltage drop in this case is going to be VBB minus VBE. Now the current going through here is going to be IB. So in this case, this guy over here, well, I've calculated, although that's actually 1.2, but I calculated for 1.5, but we're going to roll with that. Okay, so that guy is 1.79. 1.79 kilo ohms. Cool. So if I actually had a resistor that was at that exact value, I would have the exact amount of current, just barely, just to saturate it just exactly. Well, that's not enough for me. I want to try and give it way more current than it needs to saturate. That's why I'm not actually really worried about this 1.5 being 1.2 or whatever. We're going to choose a resistance that's actually a lot lower. Okay, cool. So step 4 is we're going to calculate. We're going to choose. First of all, we're going to choose a resistor, and then we're going to calculate the new current, and then that's it. So if I got 1.79, I'm not going to maybe divide it by 2, but I'm going to go pretty low. I got a 1K resistor. I got lots of them kicking around in my kit, so I'll just grab one of those and use one of those. So I know in this case is recalculate my IB with my new resistance. I'm going to take this motor out of my pocket and stick it me in the leg. Okay, here we go. So in that case, I know it's my IB is going to be, my VBB minus my VBE, that's a B, divided by the resistance, RB. And when I calculated that, I got 3.5 milliamps. Well, that's not that's 3.5 milliamps. It's hard to write over. Yeah, so 3.5 milliamps. So 3.5 milliamps is what is going to go through here if I choose a 1K resistor, and I know that I need at least 19... we just did something funky. I moved my decimal wrong. Yeah, let's go back. I can't write stuff on the board. Here we go. Yeah, I'm all better now. Yep. Okay, now that makes sense. All right. So, yeah, dude, 3.5 milliamps is a lot bigger than 1.96 milliamps. So I'm good. It's absolutely giving enough current through the base to saturate that, and that motor will be on. So, you know what? Let's add a switch. Because if we don't have that switch, the motor's going to be running all the time. So that's BJT. Thank you for bearing with me with those decimals. Yeah, I think we're good. I think you guys are good. And that's the code for the BJT. If you want to look it up, go to DigiKey and just type that in, and you're good. Yeah, that's all. Oh, goodbye.